Hello students, before I go into this new section, I would like you to refresh your memory from the previous classes. Remember that we have different types of variables, qualitative and quantitative. Qualitative being separated or classified as ordinal and nominal. Remember, the ordinal have a natural order while the nominal don't. And the quantitative, which could be classified as discrete and continuous, since quantitative is number data. It could be continuous, which means it includes decimal numbers and cannot be listed or cannot be restricted to a list. Instead, it's restricted by ranges. Or it could be discrete, which this one can be listed and does not include decimal points. It's not a number within a range. And from last class, if you remember, we went over frequencies, frequency distribution, relative frequency, and we learned about graphing techniques for frequency distributions, like a bar graph, Pareto charts, and pie graphs. This section is frequency distributions and their graphs from graphical summaries of data. Take the following data set, and let's suppose it's the student's height in a statistics class. It's just a list of numbers. But if you notice, they're not, this is a qualitative data set, but it's not discrete. This will be considered a continuous quantitative data set. Since these data are quantitative, there are no natural categories, and we cannot just make a list of all the values and then a count. You cannot do a frequency distribution the way we learned the previous class. We have to divide the data into classes. For example, if I have 4 classes, the first class from 1 to 1.24, I only have one value that falls within this category or within this class. They're not longer categories, they're called classes. 123. If I take the next class from 1.25 to 1.49, I have a total of 8 values, and we can count them. 1, 2, 3, 4, 5, 6, 7, 8, and so on. That's how we classified our numbers. We divide the data into classes, and then we count to construct a frequency distribution. So the frequency distribution is the same like it was for qualitative data. It's just that our data is now divided into classes instead of categories. Take this quantitative data, for example. It's a little bit larger. Now, this one is a discrete quantitative data. We don't have any decimal numbers. To decide what's the class width, in this previous example, our classes were given. But let's suppose we're just given the data and we have to decide what will be the class size or the class width. You have to divide the range by the desired number of classes or an approximate number of classes you would like to have, and they'll give you the class width. The range you find by subtracting the largest value minus the smallest value on your data set. I wrote it down, over here at the top. This is how you find the range, and this is our formula. Since our largest value in the data set was 52 and our smallest value was 2, I'm just going to divide 52 minus 2 divided by my desired number of classes. Let's suppose I have to have 10 classes. I want to have 10 classes. 52 minus 2 is 50. 50 divided by 10 is 5. Each one of my class width will be 5. And you start by creating all of your lower class limits, and then you create your upper class limits. Every single time you're calculating the class width, always try to round to a convenient value, and it's always better to round up. In this case, we didn't have to round, but we just so you know, in the case you have a decimal number, always round up. These will be our lower limits. And to create those lower limits, I'm going to start with first value. It can be the lowest value if you want, or it could be a number smaller than that. And then you're going to add that class size. 1 plus 5 is 6, plus 5, 11, plus 5, 16, plus 5, 21, and so on. You keep on doing that. You're going to keep on adding the class size to create all of your lower limits. For the upper limits, you're going to go one value smaller than the next class. For example, if my next class starts at 6, I'm going to end this class at 5, and so on. And if you want to, once you find your first upper limit, you can just keep on adding that class width. 5 plus 5 is 10, plus 5, 15, plus 5, 20, plus 5, 25, and so on. I put 15, sorry. Plus 5, plus 5, plus 5, plus 5, every single time. So if you want to, you can just create your first lower and upper class limits for the first class, and then you just keep on adding the class width. Here's a few definitions. The lower class limit of a class value is the smallest value that can appear in that class. So if I have a value that it's 1, that's the smallest value that can be in this class. 0 is not part of this list. I'm assuming we chose not to put 0 because we don't have any values that go as low as 0. The upper class limit is the largest value that can appear in that class. And the class width is the difference between the consecutive class limits. To find the class width, please pay attention in this little detail because it's a common question on your assignments. What is the class width? Let's suppose you're only given the classes like this. You're not giving the range, you're not giving the number of classes in total, although you can count it, but we don't know the range. To calculate the class width, just subtract one lower limit minus the previous one. 6 minus 1 is 5. 31 minus 26 is 5. 41 minus 36 is 5. 36 minus 31 is 5. But they have to be consecutive classes, meaning that it's just the next one. Same thing with the upper class limits. You can subtract 20 minus 15, which is 5. You can subtract 40 minus 35, which is 5. Never, ever, ever subtract the values in the same class. 15 minus 11 is 4. This is not the class width. The class width was 5, remember? 4 is not the class width. This is something very important to keep in mind. Oh, this was the next slide. Sorry, I forgot that I had written it down. The class width is the difference between the lower class limit and the lower limit of the next class. Not the difference between the lower limit and the upper limit, just so you know. I think it will be the previous class. It's fine. All right, so if we already created our classes, let's take this quantitative data and put it in our frequency distribution. Lucky you, I already did. The frequency for the first class is 5, then 8, then 7, then 11, and so on. If you notice, although I didn't have any values for these 3 classes, I still wrote it down. Don't ignore them. Don't delete them. You cannot have any gaps in here. Even if there's nothing in that class, you still will write the frequency as 0. So we don't have any values in our quantitative data set between 31 and 35, 41 and 45, and 46 and 50. Now, if we want to find a relative frequency, to construct a relative frequency distribution, we're going to calculate it the same way we did in our previous section. Remember, the relative frequency is the frequency in relation with the total sum of frequencies. You're going to divide each frequency for each class by the total. Our total is 40. We have a total of 40 individuals in this data set. So each of my frequencies, I'm going to divide by 40, 8 divided by 40, 7 divided by 40, and so on. I already wrote it down here. These are my relative frequencies, 0.125, 0.2, 0.175, 0.275, and so on. Remember, these are the ones that you can write down in percentages. if you want. This is the one that we use for the relative frequency bar graphs, Pareto charts, and these are the ones that we use for the pie charts more often. Now, remember, you choose the number of classes, the desired number of classes. Let's suppose I want 5 classes. I'm going to divide my range, which was the largest value minus the smallest. In this case, divided by the approximate number of classes. I want 5 classes, 50 divided by 5, 10. So each of my class widths, classes is going to have width 10. And remember, you start with the first value, and then you add 10, and then add 10 again, and then add 10 again to create your lower limits. And then the classes should not overlap. I'm going to end the first class at 10, and then add 10, add 10, add 10 to create the upper limits. Remember, round the class width to a convenient value. I know in both examples we had whole numbers, but if you end up having decimals, it's always better to round up. And just disclaimer, it's always better to round up when you're calculating the class width. We're going to do multiple calculations in this course, and it's not always better to round up. But for whenever you're calculating the class width, that's when you have to round up. All right, so for a fewer number of classes, we ended up with a total of 6 classes. Remember, we were approximating it, and this was the frequency. We still end up with 1 class having 0 frequency. And we calculate the relative frequency the same way. Our total is still 40 individuals in the data set, and I'm going to divide each of the frequencies by 40 to calculate the relative frequency. A summary of the requirements to choose classes, things you have to consider and never forget. Every observation, every individual, every value in your data set must fall into one of the classes. You cannot leave any out, and if your classes do not include all of the values, then you have to create more classes. The classes must not overlap. Notice how this class ends at 10 and the next one starts at 11. I cannot have 10 here and the next one start at 10, because if I have the value 10, which one of the two am I going to put it in? That's why the classes should not overlap. The classes must be of equal width. And this is to keep the data consistent, the data class is consistent. If this class, the width is 10, from this one to this one, the lower limits, it always has to be 10. You cannot have a class of width 5 and then one that it's width 10. And there must be no gaps between the classes. Remember how we had a few classes with zeros? Even if there are no observations in a class, even if you don't have individuals for a particular class or classes, multiple ones, you still need to include that class in the frequency distribution. And just so you can have it in a record here, these were the steps we follow to construct a frequency distribution for quantitative data. Feel free to write this down. Feel free to keep this for your record. Take a screenshot. It's up to you. We chose the class width for our data. Then we chose the lower class limit for the first class. And then we started adding the class width to create the lower limits. And then we created the upper limits by repeating adding the class width. But remember, the classes should not overlap. And then you just complete your frequency distribution by counting each of the individuals for each class. And then you just fill in your table, which we call frequency distribution. Now, if you remember from the previous section, for qualitative data, we had the bar graph, we had the pie chart, we had the Pareto chart. For quantitative data, we have a set of different graphs. The first one would be a histogram. We use histograms for quantitative data, which is very similar to what we saw on our previous section, and we called bar graph. Notice how for the bar graphs, our categories were nominal variables, And for the histograms, we don't have categories, we have classes. For the first frequency distribution that we constructed, if you remember, our classes were from 1 to 5, from 6 to 10, from 11 to 15, 16 to 20, and so on. That's how we have our classes in this histogram. 1 to 6, 6 to 10, 1 to 5, sorry, 1 to 5, 6 to 10. But you just put one of the values. You don't have to put both. Although in your frequency distribution, the classes do not overlap. Here's side by side the frequencies with the histogram. We build it in the same way as we do with the bar graph. Here's the histogram for the frequency distribution that we have with a fewer number of classes. If you notice, our graph looks different. It has less bars, but it has a very similar behavior. We have this peak towards the left, and then it's skewed towards the right. Same thing in this histogram that we constructed with fewer number of classes. A peak towards the left, a tail towards the right. Just like we have for our frequency distributions, it's the count, and the relative frequency distribution, it's the frequency in relation with the total or the percentages. Histograms based using the constructed using the frequency are called frequency histograms, and histograms constructed using the relative frequency are called relative frequency histograms. Just so you know, you can distinguish them. They look exactly the same. If you remember from our previous section, the bar graphs didn't change in shape, but our count or our ranges were the ones that changed. Okay, now here's a very important question. How do we choose the number of classes for a histogram? How do I know how many classes do I need? Unfortunately, you will have to just use your intuition. Too many classes produce a histogram with too many details. You will have too many bars, and if you have a count of 1 for each bar or very low count for each bar, you're going to end up with a long histogram that is not going to have a defined shape. If you have too few classes, you may end up having a very narrow histogram that has just like 2 bars, and you still don't have a clear shape of your histogram. There's no right way to choose your classes for a histogram. Just use your best judgment, and if you make a mistake and you cannot see a behavior of on your histogram or for your data, just start over and add or reduce the number of classes. Why is this red? Okay. Now here's a few variations you have for the frequency distributions or histograms for discrete data. Sometimes you have your classes being just one value, and we call this discrete frequency distributions or discrete data frequency distributions, and the histograms you construct with them are called histograms for discrete data. Notice how each of my classes is just one number, and the frequency is just how many times that number appears in our data set. It's still called a histogram. It's not a bar graph, and this will still be considered quantitative data. Our other example will be open-ended classes. Sometimes it could happen only on your first class or on your last class. You don't have an upper limit. You just say everything before this value or everything after this value. And this is very common when we're talking in the age ranges. If you notice, we start with like teenagers or kids, and then teenagers, and then young adults, and then middle-aged adults, and then you just put 65 plus. You don't even count an upper range anymore, just 65 and beyond. This is called open-ended class. Could be the first one, with no lower limit, or it could be the last class with a no upper limit. All right, now I was talking about the behavior of the histograms and how you choosing a number of classes affects the shape of your histogram. Let's go over the different types of shapes we have for those histograms. We call skewed a histogram that has a tail or a side that is longer than the other one. If you have a histogram with a tail to the right, we call it right skewed. And if you have a histogram with a tail to the left, we call it left skewed. Do not focus on the lump because the lump is to the left and this one will be right skewed, and the lump on this one is to the right and this one is actually left skewed. Focus on the tail. A histogram is symmetric if its right half is a mirror image of its left half, or approximately mirrored. If it looks kind of like even all across, this one will be called uniformly distributed. And if you have a lump in the middle or a peak in the middle and it falls to both sides symmetrically, this one is called a bell shape because it kind of looks like a bell. These are the 4 shapes, common shapes that our histogram could have: right skewed, left skewed, uniformly distributed, and bell shaped. There's also 2 more, but these are variations of the same right skewed, left skewed, uniformly distributed, or bell shaped histograms. Every peak or high point in your histogram will be called a mode. A histogram that has only 1 peak or 1 lump is called unimodal. And if it has multiple peaks, 2 or more, it's bimodal. It's bimodal if it has 2 peaks and multimodal if it has more than 2. I didn't include an example with more than 2, but this will be considered bimodal because it has 2 peaks, unimodal because it has 1, and if it has multiple ones, it will be multimodal. Another type of graph we have for quantitative data sets is a frequency polygon. We constructed using the exact same frequency distribution table, but we used the midpoints for each of the classes. To calculate the midpoint, you're going to find the average of the lower class limits of two classes. I'm going to add the lower class limits, 11 plus 1, and then divide by 2. That's 11 plus 1, and then divide by 2. That's 12 divided by 2, 6. That's the midpoint. And then I repeat the step for the next midpoint. 11 plus 21, that is 32, divided by 2, 16. And you keep on doing that until you find all of your midpoints. For the last midpoint, just construct a next class using the exact same class width, or just find the pattern here. 6 to 16 is 10. 16 to 26 is 10. 26 to 36 is 10. So we can calculate that our next midpoint after 46 will be 56. We use the exact same frequency from those classes. And if you want to find the relative frequency, you can too. Same thing with the histogram. If it's a frequency polygon, we use the frequency. If it's a relative frequency polygon, we use the relative frequency to construct it. And just so you can have it, the class midpoint will be the lower limit plus the lower limit of the next class divided by 2. Using those midpoints and the frequency, we're going to have this frequency polygon. We just plot those midpoint frequencies, and then we connect them with a line. This is how you construct a frequency polygon. If we use the relative frequency, the shape of the polygon doesn't change, but if you notice, our count, our frequency changed to be relative frequency. And you can write it as a percentage form or as a decimal form. Now, new definition. Cumulative frequency of a class is the sum of the frequencies of that class and all of the previous classes. And the cumulative relative frequency will be the cumulative frequency divided by the sum of all the frequencies. The relative frequency, it's always calculated the same. Whether it's the frequency or the cumulative frequency for that class divided by the total sum of all the frequencies. Here's an example on how to find the cumulative frequency. Let's take these classes with these frequencies. The first class has cumulative frequency of 13 because that's what we have so far. The second class has the cumulative frequency of 13 plus 18. I'm going to add that class to all of the previous ones. The third class will be that frequency, the frequency for that class, plus all of the previous ones. And you keep on repeating this step. Then the next class will be 3 plus 13, 18, and 5. That's the cumulative frequency. I keep on adding all of the frequencies up to that class to find it. Notice how the last cumulative frequency, for the last class should be the total sum of all the frequencies. And again, to find the cumulative relative frequency, you just take the cumulative frequency and divide it by the total. Remember that our last class cumulative frequency is the total sum of all the values, or all of the individuals, all the frequencies. So for each one of my classes, I'm going to divide the cumulative frequency by 40 to find the cumulative relative frequency. Now, we're covering cumulative frequency because there's a graph that represents quantitative data using cumulative frequency. That one's called ogive, or ogive, or frequency ogive. I forgot the parentheses. It plots the cumulative frequency, and a relative frequency ogive, or ogive, plots the cumulative relative frequency. It usually looks like a line, and it's always increasing because every class you're adding the previous classes count to it. For our particular data we had, here will be a frequency ogive, and then I'll show you the relative frequency ogive. Just so you know and keep in mind that for the frequency ogives and the relative frequency ogives, we plot them using the upper class limits. That's what we're going to have, the upper class limits in our horizontal axis here. 10, 20, 30, 40, 50, and 60, which are our upper class limits. And similarly, our relative frequency ogive uses the cumulative relative frequency. It has the exact same shape. It's just that our range on the vertical axis changes to our decimal numbers. It could also be represented in percentages. Now, to review, try to test yourselves. I want you to answer the following questions, taking a look at the following histograms. The graph represents the number of goals scored by the boys soccer team in every game so far. If you notice, we have one empty class, although our categories at the bottom are discrete, and it looks like each of our classes is just a number. This is a discrete data histogram. It's still a histogram because the data is quantitative. Now, the questions I want you to answer are: how many classes are there? What type of data does the histogram display? Which class has the highest frequency? And is the histogram most accurately described as skewed to the right, left, or approximately symmetric? This is the first review question. And for your second review question, this graph represents the data collected by students on the number of social media posts they made the previous day. The questions to answer for this question are: how many students made more than one post? and what percentage of students made between 4 and 6 posts. This is just for you to practice. And if you want more practice, I made my students in class choose one and construct either a histogram, polygon, ogive, or all of them, whether they choose to use frequency or relative frequency of the same scenarios. They can pick one and choose which graph to construct. But this is for the students in my classes. You're more than welcome to pause this video and practice constructing graphs for this quantitative data frequency distributions. Thank you so much for watching this video. Please let me know if you have any questions, and I hope you learned a lot. It was a long video. Have a great day.